Hello and welcome to today's session. We're looking at an introduction to magnetic fields. So we'll outline some of the theory, and when you're in the lab next week, we'll do some of the practical demonstrations. So we've got three objectives today: to recap the nature of the magnetic field around a bar magnet and the Earth, to understand the nature of the magnetic field around a current carrying wire, and to be able to calculate the magnitude and direction of the force on a current carrying wire in a magnetic field. So thinking back to your early days in school when you had a magnet, the magnetic field is a field around a magnet, and you could represent the magnetic field by dropping iron filings on a piece of paper and then having a magnet underneath it. And much in the same way as the other fields that we've looked at, we can represent magnetic field lines. So magnetic field lines around the bar magnet, the iron filings as you would have done when you were younger, and that's what we have. So our definition, so the magnetic field is a force field which surrounds a magnet or a wire carrying an electric current. And it's a non-contact force. Another basic recap is we've got the north and south poles, and we can call them as north-seeking or south-seeking poles. With the field lines, we have field lines radiating outwards from the North Pole and inwards on the South Pole, in the same way as we represented field lines for electric fields, so for a positive charge and a negative charge. So positive charge is going outwards, negative charge going inwards. And like poles repel, unlike poles attract. And in terms of the field lines, we think about the path. So the arrows in the field line represent the path which a tiny free north pole would take. So that's how we're specifying these field lines. So in terms of a free pole moving around that path. And if you remember in electric fields, we talked about a free positive test charge moving down the field lines. And then for gravitational fields, we talked about a mass moving down the gravitational field line. So again, similarities with all the fields in terms of our descriptions of what's happening. So moving along field lines. So the Earth has a magnetic field around it, just like a magnet, a bar magnet. We've got a north pole and a south pole, but our north geographic pole is actually a south seeking pole, and our south geographic pole is actually a north pole. The magnetic field around the Earth protects us from charged particles as well. So charged particles get deflected around this magnetic field, and that's what we have. So we can think of Earth as a large magnet. Moving on from thinking about the Earth, any current carrying wire has a magnetic field around it. Because there's charges moving through that wire, it will experience a magnetic field. So a magnetic field is generated. And we can use the corkscrew rule to determine the direction of the field, or the right-hand thumb rule. And that is another rule that we need to consider. We're also going to consider the left-hand rule, which we'll look at later on in this section. And when we get onto it for electromagnetic induction, there's a right-hand rule as well. So wires that have this electrical current passing through them produce a magnetic field. One thing to note with these rules, the direction of the current is of conventional current, which is positive to negative. So you need to be wary of this when you come to actually using these rules. It's for conventional current. Okay, so if we have a magnetic force, a magnetic field around this current, so current passing through this wire produces a magnetic field, we also get a force produced as well. So this is an example of the motor effect. And this is when the field, the current, and the force, they're all perpendicular to each other, and you get the maximal amount of force produced. I'll show you this in the lab next week. And required practical 10, your next one is to investigate how the force varies on a wire with the magnetic flux density and the current in the wire and also the length of the wire. So that's what you're going to investigate. So we'll actually see this in practice. So I'll demo it in the lab next week, and then you're going to investigate it yourselves. So when we do this in the lab next week, you can see the diagram on the right there. That's a setup we'll have. We have a top pan balance, and a current passes through the wire, and we can measure a force produced. So I'll show you that next week, and we'll see the force that is produced. But in terms of the theory around it, the size of the force is related to these things here, these factors. So the strength of the current, strength of the magnetic field, the length of the wire, and the angle between the field lines and the current. The greatest force is when we have the current perpendicular to the field, and the force is 0 when the current and the field are parallel. So that's what we'll investigate. Obviously, it's harder to show this over this recording, but I'll show you in the lab so you can actually see this in practice. Okay, so another rule that we need to know is Fleming's left-hand rule, and you'll use this for questions around this particular part of the topic. So it's a relationship between the magnetic field, the current, and the force, and we use Fleming's left-hand rule. The thumb is the direction of the force, your first finger is the magnetic field, and your third finger is the direction of the current. So when it comes to questions, you'll have to maneuver your hand around on the paper to work out the direction of the field if the question is asking you for that, or the current, or even the force. Again, for this rule, the direction of the current is conventional current, which is positive to negative. So just be aware of that in the questions that are posed to you. So the factors affecting the motor effect can be put into an equation. If we express the relationships in terms of proportionalities, we can show the equation for the force. This equation is given to you on your formula sheet. So the force is proportional to the current, also proportional to the length of wire. So we can say that the force is proportional to the current times the length of wire. And if we are given a magnetic field strength, or we're in a magnetic field, we give the symbol for magnetic field is B, so we can turn it into an equation. So F is equal to BIL. This is assuming the current's perpendicular to the field, and the questions that you'll get, they will be perpendicular, because if they're not perpendicular, we have to introduce a sine theta term, which complicates the situation. So this is the equation: F equals BIL. B is the magnetic flux density, which has the units Tesla, or the Newton per meter per amp. As I said, we can introduce a sine theta term into the equation above, but that's beyond what we look at this level. So they're all perpendicular. Okay, so typical question that you'd get using that equation. We've got an electromagnet, it's got a magnetic field of flux density 0.42 Tesla at its poles, and we need to calculate the maximum force experienced per centimeter length for a straight wire carrying a current of 15 amps placed in the electromagnet's field. So it says the maximum force experienced per centimeter length, so that is just saying that they are perpendicular, so the field and the current are perpendicular to each other, so we can use F is equal to BIL. Per centimeter is implying that it's the force per centimeter, so we can think about a length, one length of a centimeter, so we can substitute into the equation. So the magnetic field strength, or the flux density, is 0.42, current is 15 amps, 1 centimeter is 0.01 meters. Put that into your calculator, we get a force of 6.3 times 10 to the minus 2 newtons. So that's a force per centimeter. So each centimeter will experience that. The other thing to do with these types of questions is to work out the direction of the force or the field, and we'll do that next. Okay, so we've got 3 questions here where you need to use Fleming's left-hand rule to predict the direction of the force on the conductor. So if you look at the diagram for A, we've got circles with crosses. So that means the field is into the paper. The idea is it's an arrowhead pointing into the paper. And if you look at B, you've got a dot in the circles. That means the force is coming out of the paper. And then for C, it shows you the direction of the magnetic field. So for the first one, you need to point your finger into the paper or into the screen, because that's the direction of the field, and then the current is going up, so you need to orientate your finger around. So there's quite a lot of manipulation of the direction of your hand. Then for the other one, for B, the field's out of the paper, so you have to rotate your hand around again, and the current is going downwards. So again, rotating your hand around. For C, the field's going up, and the current is going towards the right, because the arrow on the conductor shows that. So have a go at trying to work out which direction they are, and then I'll put the answers on the board. So if you manage to get them correctly, so A, push towards the left, so fingers into the paper, first finger into the paper, second finger upwards, directions to the left. B, outwards, so your finger has to point out. The second finger is pointing downwards, so again it's towards the left. And C, we've got the field pointing upwards, so that's up, first finger up, and second finger to the right, so that means it's pushed out towards the paper, so the thumb is pointed towards you, or out towards the screen, should I say. So that's the type of questions you'll have to deal with left-hand rule. So finding the direction and calculating the force. You may have to calculate the magnetic flux density or the current or the length of the wire as well. So your task is to complete summary questions 24.1 and upload them via Turnitin. Again, if you have any problems, message me via Teams or drop me an email. And you can also try the chapter 24 exam style questions. So there's some more challenging questions to try for chapter 24. Those are available on LearnZone.